Let's talk about a mind-boggling material that's about the pulmonary ventilation, but specifically intrapulmonary pressure, pulmonary pressure, and transpulmonary pressure. Let's go there. So there's a pressure that is in the atmosphere at 760 millimeter of mercury at the sea level. And then there is a lung, right? So it's a chest wall, right? And this circle represents lung, and especially in the lungs alveoli, those pockets, that's where the gas exchange happens. So the gas exchange happens between the alveoli and the blood vessels that wrap around the alveoli. But we want to talk about the pressure differences. So here's the atmospheric pressure, 760 millimeters of mercury. Inside of the lung, in the alveoli, the intrapulmonary pressure, right here, we're going to define it P-pul, pulmonary pressure, let's say is also 760 millimeters of mercury. So it basically equalizes the pressure. At one point, the pressure would be equalized with the atmosphere and what's inside of the lung. And then there's a pressure between the lungs and the chest wall. So this is the visceral membrane, and this is a parietal membrane, like that wraps around the chest wall. And here's the membrane that wraps around the lung, visceral and parietal membrane, or parietal pleurae, and this is the visceral pleurae. So the pressure here in this pleural space, that's a little space here, -4 compared to what's inside. So it's basically, in pleural space, it would be 756 millimeters of mercury, -4. And this pressure is called intrapleural pressure. So now let's talk about the mechanics. So during inhalation, what happens that here is a diaphragm. So when we breathe in, we expand the chest wall, and this muscle flattens like this, right? When it flattens, it creates more space within the lungs. So the lungs inflate, and it's easier for the air to get inside. So the pressure inside of the lungs drops. From 760, it drops down. So now the intrapleural pressure, P-pul, is about 758 millimeters of mercury. Right? There is also something happens with the pressure here, intrapleural pressure. The intrapleural pressure becomes more negative. It was -4, now approximately it's going to be -6. So the physiology within the lungs is very interesting. So there's water particles, and what happens, it creates cohesion. So the water particles try to stick one to another. So here's like one water particle, right? Hydrogens here, and the oxygens, partially positive, partially negative. And there's another water molecule, right? Hydrogen, and there's another hydrogen, and there's the oxygen. So here, water molecules create hydrogen bonds, and this phenomenon creates a surface tension. So the lungs naturally wants to recoil, they wants to collapse. So that's a natural pressure, 758 approximately. When we expand the chest, lungs inflate, they become bigger, the diaphragm contracts and creates more space. Pressure drops. There's also elastic membrane in the chest wall that also has this physical ability to create outward pressure. So it's basically the chest wall is trying to pull the lung out from collapsing. So it basically prevents the lungs to collapse. So lungs create inward pressure, and within this space there's a creation of outward pressure. So it's like a tug of war. So intrapleural pressure prevents lungs to collapse. just because there's also elastic tissue within the chest wall. So what happens with exhalation when we exhale? So we want to go back to the original state. So here's the chest wall, here's the lung, and we go back to -4. It's all approximate, -4, and we slightly, when we exhale, we need to generate more pressure. So the diaphragm relaxes and it creates a dome shape, so there's less space in the lungs, so there's more pressure and it helps to get rid of the air. So the pressure, intrapulmonary pressure, let's say now it becomes 762 millimeters of mercury, and atmospheric pressure is 760 millimeters of mercury. So that's atmosphere, right? And it's easier for us to get rid of air. So you go down concentration gradient from high to low. Same thing with inhalation. You go down concentration gradient, right? You go from 760 to 758. So here we expand the lung, pressure drops. Here we contract the lung. We generate more pressure and it's easier for us to get rid of air. I'm not talking about carbon dioxide and oxygen, we're just talking about the air. The important key here is that the lungs, the alveoli, are made of elastic fiber. It's like you're stretching the rubber band and it constantly wants to recoil, come back to its original shape where it's comfortable. Same thing happens with the lung. But this is countered by the chest wall. There's also elastic tissue. There's pulling outside, so it prevents lungs to collapse. So, and here, right, we slightly can go back to -3 or -2 approximately. Usually it doesn't really go to -2 in healthy body. Exhalation gets to 762, but then it goes back to its original 760 to equalize the pressure at one point, right? We're not talking about physical activities. So there's a Boyle's law states, if the pressure increases, volume decreases. This is inverse relationship. If the pressure decreases, the volume increases. So with exhalation, the pressure increases here and volume decreases, or let's say volume decreases first and that's why the pressure increases. In inhalation, that's vice versa. So the volume increases and pressure decreases. If it's hard to understand, just think of the water, right? So here's the water. So what's going to happen if this container all of a sudden becomes wider, like this? So the water drops, right? So the pressure drops. So now it's more volume, same amount of water, but the pressure drops. So air goes down its concentration gradient. So let's talk about pulmonary ventilation, but now I want to introduce here oxygen versus carbon dioxide. There is a ratio between oxygen and carbon dioxide. It's not 1-to-1, but what happens is that there's more oxygen in atmosphere compared to the oxygen in the system, right? There's less oxygen in the system. So when we inhale, it's easier for the oxygen to get inside of the system, so it goes down concentration gradient. But when we exhale, there's more carbon dioxide in the system compared to carbon dioxide in the atmosphere. So when we breathe out, it is easier for carbon dioxide to get out because, again, you're going from high concentration to low concentration. Same thing is here. You're going from high concentration to low concentration. So, and transpulmonary pressure, basically this equals pulmonary pressure minus intrapleural pressure. That's a transpulmonary pressure. Differences here. So what happens within the lungs, we have cells that producing a surfactant. Alveolar type 2 cells. There's also alveolar type 1 cell that helps to exchange the gases. And there's alveolar type 2 cells. So this alveolar type 2 cells, what they do is they produce surfactant. Just because here water molecules stick one to another and they create this surface tension and they create this pool. So the alveolar surfactant type 2 breaks down this hydrogen bond that prevents from water molecules to constantly being connected one to another, and it slightly relaxes the surface tension. Otherwise the lungs will collapse, because the lungs always try to collapse, but this counteracts. So this pressure, interpleural pressure, this is the outward pressure, outward, and pulmonary pressure, intrapulmonary pressure, is inward pressure. So, and this is usually the concept that is really kind of hard for students to grasp about the pressure. So if it's hard for you to understand the pressure, think of water. What's going to happen with water if you're going to put it in the container, but then all of a sudden you're going to create more space in the container? Think of the balloon. When you put the water inside of the balloon, you stretch the balloon, pressure drops. You start creating the pressure in the balloon, the pressure increases. And this is the Boyle's law. So when the volume drops, pressure increases. When the volume increases, pressure decreases.